All right, gang, Math 5500. Made a silly mistake putting up the video previously. And I just don't feel like rewriting everything, so I had it written out in the previous video. So I'm going to be a little lazy here and um, just use what I had written out and just go through it. That's going to help because I want this to be a brief video. So where are we? Okay, we're starting lesson number 3, and you just submitted assignment number 1. I think it's a good time to just pump the brakes a little bit and review a few things and build on a couple of things as well. So again, this video should be brief. I noticed, and you may, if you teach math, if you've been teaching long, if you teach a course repeated times, I think it's kind of second nature to focus on things that students tend to struggle with. Uh, having taught this class before, I can tell you that students still continue to struggle with y sub I versus y hat sub I. The y sub I is the observed y. I have a small data set here that I'm going to do some illustrations with in just a second. So the observed y's would be 5, 12, and 10. The predicted y's would be what we would get if we put 20, 55, and 30 into our model. Now, usually the observed y and the predicted y are different, uh, thus the need for the error term. So make sure you tattoo the differences in these, tattoo those to the brain. Now, in estimating beta 0 and beta 1, uh, in other words, calculating B0 and B1, an approach that I don't think I've provided previously, which is a little strange because if I was on a deserted island and didn't have some method of technology in, to get off the deserted island, I had to calculate beta 0 and beta 1. It's kind of goofy. But anyway, I would use this estimate for finding beta 1. So it's just the products of the deviations for x and deviations for y. Sum those up, and then sum the deviations for x squared. And I've illustrated that with r. So what I would do here is I would take the numerator. I just called it the numerator because I'm not that clever with naming things. And then the denominator, I would just take, again, the deviation squared. And then I could create B1 by just taking the sum of the numerators divided by the sum of the denominators. You can see here that the estimate is 0.177. Now, to calculate beta 0, again right here, the mean of the y's minus B1 times the mean of the x's. And we can see the beta 0 is 2.808. All right, we can validate that, if you will, using R, the LM function, and we can see that we get the same thing. It's a good thing because it would be kind of goofy regression in statistics if I showed you something that didn't work. If we want to calculate the mean response, something that I would want you to think about, could we calculate the mean y for an x of 60? I say no, because the bounds of the domain of our x values, the range of our x values for which this model was made, go from 20 to 55. So I feel comfortable making predictions from 20 to 55 because I don't know after we reach an x of 55, I don't know what the model does later. It may do something really wacky like this. It may continue in a linear fashion. I just don't know. I wouldn't hesitate so much to calculate, probably, I'm going to contradict myself just a little bit. I wouldn't hesitate as much to predict the mean of y for 60 because it's just outside the bounds. But if I got into 70, 80, 90, something that's quite a bit higher than the upper bound, I would not feel comfortable. So again, if I want to calculate the mean response for x equals 50, plug it in my model and go for it. Again, y sub I versus y hat sub I, so the predicted is 5. But if we want to put 20 in our model, which I did right here, notice we get 6.41. So this tells me that my error term, so the observed is 5, the predicted is 6.41. So my error term would be, so it'd be the observed minus the predicted, so it'd be minus 1.41. That's the value it takes to make the observed and the predicted equal. Now, we talk a lot about errors, residuals. Again, residuals are just the observed y minus the predicted y. A few interesting facts here. The sum of the errors will always be equal to 0. The sum of the errors squared will be minimized. That's the purpose of the maximum likelihood estimation process. Well, no, I'm sorry. But it's the process of the least squares approach, more applicable. Interesting fact that I may have you prove someday on a test, hint, hint, is that the sum of the y's will be equal to the sum of the predicted y's. Interesting fact. Another interesting fact, if we multiply or if we take the product of the x's and the errors, sum them up, take the product of the predicted values and the errors and sum it up, these will all be equal to 0. Another cool fact that you probably proved or will prove is that x bar, y bar will always be on our regression line. And just a little extra, a little bit icing on the cake. If we want to prove that the errors will be equal to 0, we start with the sum of the errors, rewrite errors as the observed minus the predicted, rewrite the predicted as y sub I minus the quantity beta 0 plus beta 1 x sub I, distribute the negative, and then we get this relationship right here. Well, when we looked at the normal equations in a previous video, we got that the sum of the y sub i's would be equal to n beta 0 plus beta 1 sum of the x sub i's. So therefore we know that this whole term has to be 0, proving that the sum of the errors must be equal to 0. I got more stuff, but I think, again, I just wanted to pump the brakes a little bit. So the purpose of this video was just to make a few things clear that need to be very clear as we move on. So I'm going to end this video. So guys, take care.